This is a question on the method of least squares, and I wanted to go over why the method works. Hopefully a lot of you already know the method, but what I want to emphasize is why it works and what is the role of this theorem in making it work. And this is really the theorem that does all the heavy lifting for you. Let's just go through the question. You have a farmer who fertilizes 4 fields with different amounts X of fertilizer and gets different yields Y. The 4 fields yield 1/2, 1, 5/2, and 3, and the respective fertilizer amounts are 0, 1, 2, and 3. And I've just plotted that down on this graph here. Find the line of best fit, y equals ax plus b. Well, I've called it mx plus b out of habit. So let's change the question. Mx plus b through the line through these points. Hence you estimate the field. Let's just find the line of best fit. You can do the rest. It's not immediately clear that this is a question about algebra or how even this theorem, this wonderful theorem, fits into it. So first of all, let's just plot the graph. Here are the points. In orange, the orange distances are the errors. And errors in our approximation. And the idea is you minimize the error. You want to minimize that orange distance. Okay, let's set this up as a system of linear equations, which is what we have here. A system of linear equations. Okay, so this is starting to feel more like a question we could solve with linear algebra. But unfortunately, this system of linear equations doesn't have a solution. You can take this system here and you can represent it as a matrix. That is ax equals y, where a is this matrix, b is the 2 parameters you're trying to, the point intercept and your gradient, and y is the values you're trying to achieve. But unfortunately, there's no solution. There's no solution to that. Bad times. Why is that? Well, it's because y is not in the column space of A. You cannot make this vector y as a linear combination of the columns of A. That should be transpose. You cannot make this vector y as a linear combination of the columns of A. Instead, so as a picture, you can imagine this kind of grid with the red and blue lines. You can imagine this grid as being the column space of A, otherwise known as the space of all possible values that AX can take. So you toggle X, and you can get anywhere on this 2-dimensional grid just by toggling X. But you can't get to Y. Y lives outside the grid. So you don't just give up. You say, okay, well, if I can't get to Y, what I'll do is I'll get to the closest point I possibly can. This point here, which lies on the grid directly underneath Y. That'll do. That'll be the bit that minimizes the length of this orange line, and the length of this orange line is of course related to these errors that we had before. So if we can't get to Y, we'll get the next best thing, which is the value AX, which is closest to Y. Now, the value of AX, which is closest to Y, is the one that makes Y minus AX perpendicular. It's the perpendicular distance. This means that Y minus AX is in the, so that's the orange vector, is y minus ax is in the column space of A, but it's perpendicular to it, which is, by the theorem, the kernel of A transpose. Now we're cooking. because when you know it's in the kernel of A transpose, you could take this vector, that's this vector here, and bust A transpose on it. That produces this equation here, that because you don't really care what that is. What you care about is that when you take A transpose of that stuff, you get 0. Then you arrive at this equation here, and this only has one unknown in it. This only has the X unknown in it, and so you can figure out what X should be just by figuring out what A transpose A is, A transpose Y. You arrive at this equation, and at this point, Robert is your father's brother. You've got a system of equations you can solve. And it's just row reduction to find out what the values of B and M are at this point. So of course you could probably do without the director's cut and just go straight to this after a few words. But I really wanted to motivate why this works. And it works because it's essentially geometry. There's no you don't have to use calculus to do this. This orange distance here is minimized when you have y minus ax perpendicular to the column space of A, which puts it in the kernel of A transpose. So that's why it works. Of course, you can just take it from this step onwards and go down to get the solution. But I wanted to talk a little bit about why. So there you have it. I hope you enjoyed the video.